Okay, and we're recording. So after last time's very high level introduction, today's when I start getting into one of the three main PDEs that we're going to look at all semester long. Because as I mentioned last time, we have heat equation, wave equation, and then Laplace's equation. So today we'll start looking at the heat equation. I'll get the old screen share going. Okay, so doing a few lessons at once, but these lessons are actually from the textbook are actually pretty short. All right. Now, let's see. All right. Oh, okay, at least we have most people here. So what I'm going to do is describe at least a one-dimensional version of a typical problem that we'll be looking at that happens to involve a PDE, but also additional conditions prescribed to ensure that there is a unique solution. So what we're studying is heat flow within an object, and because we want to keep it simple with just one dimension, that object will be a rod of length L, and we want to limit this to heat flow in and out only at the ends. So to just have heat flowing through the rod, so that we don't have heat flowing out the sides. Okay. So we assume that the rod has some fixed temperature T naught at the start, and it's not necessarily a constant temperature throughout the rod. The point is that the initial temperature at every point within the rod is known. Okay. So then we prescribe that the temperature at the endpoints of a rod are some known temperatures T1 and T2. Okay. So here we have what is called an initial condition, to what the temperature throughout the rod is now, and then boundary conditions, what the temperature is at the endpoints. So given those conditions, and based on physical laws, how does the temperature throughout the rod change over time? And that is what the heat equation is meant to tell us. So we have a problem with three components. First, the PDE, and that's what we have here. This is one of the simplest forms of the heat equation. So first derivative with respect to time is some constant alpha squared, which I'll discuss later, times second derivative with respect to x. And here's the domain of a PDE in space and time. So we're just interested in the interval from 0 to L. That's taken up by the rod, and then time starting from now until forever. Now, one way to give a physical interpretation of this PDE is actually by using an approximation to the second derivative. Now, here I'm approximating a second derivative by a center difference. Now, unless you've taken one of my numerical analysis classes, you may not have seen this center difference before. But I'll give a quick explanation of where it comes from. So I'll just fill that in here. And as usual, the final version of these notes is what I will post later in Canvas, and also on my own website later today. Okay, so we have, because if you use a definition of derivative, And this comes from the familiar difference quotient that you would remember from a difference. So here we have a what's referred to as a forward difference because it's x plus delta x and x that we're using to estimate the derivative. But we also have, if we just replace delta x with minus delta x, a backward difference. So if I start with this forward difference that approximates du dx, and then I apply a backward difference to each one of these, so really what I'm doing is I'm taking the second derivative then, because I'm differencing the difference. This is exactly what I would get, this center difference here. And those of you have taken like Math 460 or 560 would have seen that there. So then what I can do, I can fill this in for uxx and rearrange, and this is what I get. And what have we here? Here we have the average of temperatures at points that are neighbors to x. So x plus delta x, x minus delta x. So what happens if U is less than the average of surrounding temperatures? Okay. So, and that's something I should have mentioned earlier. I'll fill that in here. That U refers to temperature. That if the neighboring temperature, the average of neighboring temperatures is greater than temperature at a certain point, then this quantity will be positive. Therefore, the temperature is going to increase. Whereas if the temperature at a certain point x is greater than the surrounding temperatures, then we have du dt being negative. Therefore, the temperature at x is going to increase. Going to decrease due to this being negative. So we can think of this as describing the direction of heat flow into x based on this comparison to temperature at neighboring points. Okay. Another way to think of it is, as you would know from calculus, that the second derivative represents concavity. So if a temperature at this point is concave up, then it's going to increase. Otherwise, it's going to decrease. All right. So here we have a PDE that's a first component of this problem that models how temperature is going to evolve over time. Here we have the boundary conditions that the temperature at these points, x equals 0, x equals L, is specified to be these given values T1 and T2. There are other kinds of boundary conditions that we'll talk about later today, but this is one kind. And then we have initial condition that the temperature at the current time throughout the rod is specified to be T0, which in this case, in this example, T0 is a constant, but it could be any function of x. Right. So these three components, the PDE, boundary conditions, initial conditions, make up what's called an IBVP, so initial boundary value problem. So we need all of these components to specify the solution uniquely. All right. Here's some other examples, variations of the heat equation. So in the example I set up, the sides were assumed to be insulated, but suppose they're not. Suppose there actually is heat loss out the sides. So that would be accounted for by this additional term here. So if the temperature within a rod is greater than a surrounding temperature, then this whole term is going to be negative. So that's going to be contributing to a decrease in the temperature going forward. And a heat gain similarly if the temperature in the rod is less than the surrounding temperature, which makes sense because, as we know, heat flows from regions of high temperature to regions of low temperature. You may also have additional terms describing a heat source. So we have the inhomogeneous equation with this source term f of xt here, and we'll first learn how to solve a heat equation, just this part, and then we'll learn how to account for this, a term like this a little later on.
Okay. Oh, shit.
I think someone needs to be muted, or unless they have a question. Okay. All right. And then if we have a first derivative term, can account for convection. So here's some examples of convection that occur. So there are a lot of problems that involve diffusion terms with UXX, convection terms that involve first partial derivatives, and sometimes a reaction term that would just have a coefficient times u with no derivative involved. So convection or advection, diffusion, reaction problems are common in a lot of applications. All right. So those are variations on the PDE. Now I want to talk about variations on boundary conditions. So the first type of boundary condition, which I want to mention the name of it. These are called Dirichlet boundary conditions. And this is where the solution is prescribed to have certain values at the boundary points. So these could be any functions of time, but they don't have to be constant. All right. Let's see. Okay. Actually, I'm gonna skip around here to type 3, then I'll come back to type 2 because that way the names will make more sense. This type of boundary condition, it's called Neumann, where the first partial derivatives of a solution instead of u itself are specified to either be 0 or it could be equal to functions of t, like in the case of Dirichlet conditions. And the first derivative refers to flux, which is a flow rate of heat energy per unit area. That's how flux is defined. So we're specifying u, that's Dirichlet. If we're specifying first derivative of u with respect to x, that is a Neumann condition. So in one dimension, we just specify whatever boundary condition is at the two endpoints of our interval. If we're in higher dimensions, instead of like du dx or du dy, it's the normal derivative. So it's derivative in a direction that is normal or perpendicular to whatever boundary of your domain that you have. And then type 2 is so here we're dealing with both u and du dx. So these are mixed boundary conditions, also known as Robin boundary conditions. So for these boundary conditions, we're using Newton's law of cooling, and Newton's law of cooling describes the outward flux at the endpoints, at the left endpoint and the right endpoint, based on whatever the temperature of a surrounding medium is at that endpoint. So it's some heat exchange coefficient times the difference in temperature. So then we combine Newton's law of cooling with Fourier's law of cooling that relates the outward flux at each endpoint to the inward normal derivative. So when we're at x equals 0, then when x is increasing, that is going into the domain. So we have this thermal conductivity coefficient, and then the du dx, which is the normal derivative in this case. But then at the right endpoint, x equals L, the derivative with respect to x, that's going out outside the domain. But we want the inward normal derivative, and that's why we need the minus here. Now, what about flux more generally? How we define flux? Oh, you know what? I just realized I've spotted a mistake, and actually, it's a mistake in the textbook that I happen to copy here, and I'm going to eliminate. That A should not be there. Okay, so flux from left to right is defined as minus k du dx. So the reason why it's defined that way is that let's suppose that du dx is negative. Then heat's flowing from left to right, because what's happening is du dx is negative. That means that U is decreasing. The temperature is decreasing as we go from left to right. And because heat's flowing from high temperature to low, then we have heat flowing from left to right in that case. And then multiplied by minus K, when we have heat flowing from left to right, then flux from left to right will be positive. So that's why it's defined that way, to be consistent with the fact that heat always flows from high temperature to low. Okay. Now, as I mentioned, flux is defined as flow rate per unit area, so that's why that A was not supposed to be there. A is a cross-sectional area of a rod. Okay. So these are three very commonly used types of boundary conditions that we can have. And the thing is, you can have different boundary conditions at different endpoints. So as an example, and one of the homework problems gets into this. So what if you have a situation where one end is insulated, but the other is immersed in water with a constant temperature? So there's a certain, so whatever the temperature of a water is, that's the temperature of a surrounding medium at that endpoint. So you're going to pick and choose from the types of boundary conditions which is the correct one for each boundary point. So that's something that can certainly happen. Okay. Are there any questions up to this point?
No, I don't have it.
Okay. Oh, everybody's here now. Good. All right. So what I'm going to show you now is mathematically how the heat equation, or at least this form of it, can actually be derived from physical laws. So here we have a PDE, same situation with a heat flow in a rod of length L. So we have this diffusion coefficient, and that this is going to be defined as a result of deriving this equation. And then we have this external heat source, capital F. All right, so some assumptions that we make, that the rod is homogeneous, so it has a uniform, constant density, lateral insulation, so we only have heat flow within the rod, not out the sides, and also that the temperature within any cross section is constant. So, so this simplifies the manipulations that you make. Now, if those assumptions are not true, yes, some kind of a PDE will still be derived. It'll be a more general form of this, but I'm just making these assumptions just to not have a derivation too cluttered with complications. Okay. But basically, we want to be able to treat this as a one-dimensional problem. So we only have to think about du dx with respect to x as opposed to other variables. Yeah. But I'll talk about multidimensional case afterwards. So what we're doing is we're focusing on some arbitrary segment of a rod. So starting from x and going up to x plus delta x. And we're just applying conservation of energy. So the heat energy within the segment satisfies this principle that the net change in that segment is going to be accounted for by two things. The net flux across the boundaries, so entering in from the left and also from the right, and also any heat that's generated inside the segment. So only those two things can account for the net change within that segment. So the amount of heat within that segment is defined here. So if we have an arbitrary segment AB, I can hear someone tapping a lot. Okay. Thank you. Okay, is defined by this integral. So here we have the temperature at any point within that segment. A is a cross-sectional area. C is the specific heat, and I'll say a term I've not used since, not heard of it since my 8th grade science class, way back when Reagan was president. And then rho refers to the density of a rod, and this is why we assume that certain things are constant, like a temperature not varying within a cross section, or the rod being made of a homogeneous material, because then that means that U is a function only of S, which is playing a role of the X variable here, and also means that rho is constant, and also C is constant in term also because of a rod being homogeneous. Okay, so flux from left to right is given by minus k du dx. So the conservation relation I had before, if I take this equation and I take the derivative of both sides of this with respect to time, the rate of change of the total amount of heat with respect to time is just going to be this integral, except differentiating with respect to t. But the only thing here that depends on t is the temperature U. So on the left side, I just have, so that's the derivative of that previous integral with respect to t. And because c, rho, and a are all constants, pull them out. Okay. Now, the net flux across the boundaries, remember flux is a flow rate. So that's what leads to these terms here. and I have minus k ux, and that's flux is I mentioned the flow rate, but it's also per unit area. To get the total flux, I multiply by the cross section area, and then that's for the left endpoint. For right endpoint, I need inward flux, but left to right, when I'm at the right boundary, it's going outward, so I need to negate it. So that's why I have positive KUX for the flux in that case. All right. And since flux is defined as per unit area, multiplying by A gives me flux across the entirety of the ends of the segment. And then I account for, so F is the amount of heat generated per unit length, per unit time. So I just had to integrate that over a segment and then also multiply by A there too. So now I have this resulting from conservation of energy. And I have A all across the board, so I can cancel those out. But now what I'm going to do with this, here I have integral from x to x plus delta x here and here. I'd like to have the same thing here, and I can certainly do that because I have a difference of function values at x plus delta x and x. So I can write this basically applying a fundamental theorem of calculus in reverse. So this difference here is equal to the integral of a derivative of this with respect to x. And that's what gives me this integral here. So now I have everything integrated from x to x plus delta x on both sides, or I could just rearrange, and I have this. So now we have this integral equaling 0, but on an arbitrary segment of a rod. When the integral of a function is 0 over an arbitrary segment, then the integrand must be 0 throughout the entire domain. So for convenience, I'm dividing by c times rho. So k over c rho is a positive constant, which I'll call alpha squared, to reinforce that it's positive. And then I define capital F as little f divided by c rho. And because all of this must be equal to 0 throughout the domain, this is what I get for the final PDE. So this is how PDEs are derived in a lot of situations. So we have some physical law, such as conservation of mass or energy, that results in an integral equation, like the one we saw above. And then if we can express it as an integral over an arbitrary subdomain of some quantity being 0, that whole quantity must be 0 throughout. So then we are able to drop the integral and arrive at the actual PDE. So that's how this derivation process for all kinds of PDEs plays out. Okay. All right. So that is the derivation of a heat equation. I remember when I taught multivariable calculus, actually deriving the heat equation of multi-dimensional setting. And so the main difference comes about in this step right here. So here I'm in one dimension, so I'm using the fundamental theorem of calculus. If this was a two-dimensional domain, I'd be using a theorem that you may remember from when you took multivariable calculus called Green's theorem. If I'm in 3 dimensions, I'm using the Gauss divergence theorem. If in a more general setting of any number of dimensions, it would be the general Stokes theorem that covers all of these cases. So all of this applies in any number of dimensions that you're just not needing to make the exact same assumptions. As you remember from Wednesday when I showed you the heat equation, it was du dt is equal to Laplacian of u, where we have Laplacian defined appropriately for however many dimensions that you have.
All right. Are there any questions about what happened during this derivation? Okay. Now, I'm quite surprised to find that I've gotten through all these notes in a lot less time than I expected. Put it that way. So I thought, oh, 3 lessons in one day, that's a lot. I'm probably going to consume the whole time. I might not get through the whole time, but no, bam, it's all done. I guess I should have seen that coming because in the last class period before this one, I went through 9 pages in a class period, and here I only have 4. So, whoops. So, now, I don't suppose that anyone's happened to start the homework because I gave problems from lesson 1, but I think they're not. If I refresh my memory as to when they are due. Okay, well, lessons 1, 2, 3, 4. So everything I covered last Wednesday and today, the homework for that is due on Monday, February 1st. So I'm guessing that nobody has gotten an early start on that. But if anybody has and has any questions, like from a lesson 1 part, there's just plenty of time to ask.
When I went online, I think it was still unpublished or locked or something like that. So I don't know if it listed what the actual problems were. I
Okay,
don't know if that's changed yet.
let me check.
Because I did try to go look once you posted the book.
All right, when I look at the assignments, all of those say published.
It doesn't show in Canvas, but it shows on the other course webpage.
Oh, okay. Well, yeah, that's a whole other system. But okay. So what exactly are you saying does not show?
It just says the module is unpublished so that you can't see the assignments.
Okay, so maybe so even though the assignments are okay. Oh, I see. Okay, so the actual modules could. Okay, one thing I want to check if anyone's in
Sorry,
Canvas.
I probably explained it wrong.
Okay, if anyone's in Canvas, can you click on the left? Can you click on assignments and let me know if they are there?
Yes, sir. The assignments are there. You can see all of them, but when
Yeah.
you do click on one, it says what she said earlier.
Okay, so now, yeah, because I'm on the modules page, and those are, except for week 1, it only has a syllabus. Those are unpublished. Let me go ahead and publish all of those. So you're saying that when you click on the assignments, it won't show it to you. That's really weird because you think, well, the assignment itself is published, so what's the problem? But I'll just publish all the modules anyway because why not?
It's showing now. Like it's popping up as you're doing it because I clicked on assignment 1 again, and it finally listed like lesson 1 and what problems, and the modules are open as well.
Okay. Yeah, I didn't realize that by not publishing a module that the published assignment would not be visible. So they actually told us this semester, so starting now in the spring, that we have to organize things by modules. that's a new thing for us to be required. So I was like, okay, fine. Okay. Any other Canvas difficulties I should know about? Okay. I actually never used Canvas that much before COVID came along, but okay. All right. And yeah, there's always the other site that is outside of Canvas that it is mirroring everything here. Okay. Alrighty. Well, I think we're going to have a short class here, unless anybody has any other questions.
I have a question.
Okay, because let's say I bet a lot of people are like, please let no one ask questions.
Yeah, I'm the worst.
I want to hear it. So
it should be short. It should be short. It's just from the lesson 1. Is there and it's actually question 1, but at the very end of class we talked about the parabolic, hyperbolic.
Yeah.
Those sorts of things. Is there an elliptic? Is there a better way? I guess that was the only part in the question 1 I couldn't necessarily, even though there's kind of solutions in the back of the book or whatever, and I could compare to them. That was the only one that would kind of get to me. I don't know.
Okay. So looking at lesson 1, question 1.
So just that like last. Well.
Oh well. Well, for one thing, let's see. Okay, yeah, actually, the last equation in this bunch cannot be classified that way, because it has to be second order. It has to be linear. Okay, so basically, you're having trouble classifying those as either parabolic, elliptic, or
right.
Okay, so first thing is to fit the form of a general second order equation that's given earlier. If you make sure that all the terms involving u are on one side of the equation, anything else on the other side, okay. And then elliptic, parabolic, hyperbolic, it's going to come only from the second derivative terms, because it deals with the coefficients a, b, and c for those terms. And for equations a and b, these are equations involving x and t. So you're going to have so t is playing a role of y in the general discussion of these classifications. So it's just like whatever the other variable is. But what's going to happen is, like in equations a and b, for instance, you're only going to have one second derivative term, the uxx. So since the other second derivatives are missing, like uxt or utt, you don't have those, then 2 of the 3 coefficients are going to be 0. So part C is going to be more interesting in that regard, because at least you have all 3.
Okay. So that's okay, because the second derivative is clearly going to be 0 on some of these other terms. It's pretty easy to see it's like parabolic, but
yes.
Okay, cool. Nah, my bad. That's all.
I was going to say, hey, don't give it away, but then I realized, well, it's in the back of the book. So.
Oh, sorry. Yeah.
Okay.
Keep my mouth shut.
Okay.
It is in the back, so.
Points for you, though.
Oh man.
All right. Well, at least someone's getting started on the homework. All right. Any other? Okay. Well, this shouldn't happen again, but you never know. Getting through everything as quickly. But again, I think I have a similar number of pages for next time, but there's also going to be a whole lot more actual math involved too. So okay, we'll just see what happens. Okay. Well, if it's going to give me more of a chance to get these things posted sooner for this class and also my other one and several of you are in. So, okay. Well, then I will stop recording at this point and I will see you in a couple days.